The purpose of video number 3 is to discuss validity as it's measured in terms of, again, test measurements. So we're not yet at the validity of a study, we're still working on the validity of a measurement. Normally we use many different methods to provide evidence of validity: content, criterion-related, and internal structures, because you cannot talk of the validity of any one test. Everything is really dependent on the participants, the situation, and so on. So if you validate a test for youth, you can't guarantee it would also be validated for adults, and vice versa. You can't assume that something that is validated for elite adult athletes will also be validated for recreationally trained adult athletes. You have to validate in those situations. You also often want multiple different types of methods to kind of serve as a way to triangulate or confirm validity from a bunch of different areas. So we're going to examine those different areas in this PowerPoint. The historical definition of validity is the extent to which a study measures what it purports to measure. In this case, a measurement does. But really, the understanding of what that means is unclear. In 1999, the AERA kind of provided a more clear definition that's been used in the research since, where it's the degree to which evidence and theory support the interpretation of test scores for the purported use of the test. So what that means is whatever numbers you're getting back, whatever you've quantified, really has to make sense in terms of what we know in the theory and the literature. If you get a number back that makes absolutely no sense based on what you know about that variable, then that might tell you that something's wrong with the measurement, not necessarily wrong with your sample. So you have to kind of take these numbers, step back and say, what does this mean in terms of what you know about the science, the empirical literature, the theory in sports psych and teaching admin, it's more of a theory-based, whereas in ex-phys it's more of a science-based. Does this all make sense based on what you know? This is done, when dealing with hypothetical constructs, and kind of in physiology, this is kind of done sort of, you're using proxy measurements to understand mechanisms that are happening in the body that we can't go into the body and measure directly, but we can sort of make some inferences about what we think is happening. The same thing, you can't go up to a person's brain and measure their creativity, but we can make some inferences about their creativity with a paper and pencil measure. So the first one we're going to start with is content-related validity. Content validity we measure in 3 different areas: domain clarity, content relevance, and content representativeness. This can be done through both a qualitative and quantitative manner using a panel of experts. Domain clarity is making sure that your operational and constitutive definitions of the hypothetical construct make sense, and they actually match up with the theory. So if you're going to be measuring something new, you need to make sure that other researchers in your area will look at it and say, yes, we agree that the way that you are constitutively defining it makes sense, but also the way you're operationally defining it. If there are multiple domains in one instrument, for instance, if you have a questionnaire with 4 subscales, each subscale has to be defined separately as well, to make sure that the items match up with that one subscale's domain and then the overall construct you're trying to measure. Content relevance and representativeness are 2 sides of the same coin. In content relevance, you want to make sure that all of the parts of the test or all of the items are relevant to what you're trying to measure, so nothing is in there that shouldn't be there, where content representativeness is making sure that everything should be there is in fact in there. So it's really scrutinizing all the different parts of the test or all the different items and making sure we get rid of things that don't belong, that's content relevance, and making sure we include things that do belong, that's content representativeness. Here's an example where we're going to do content validity. Now we want to validate a test in research methods. We consider the test time and the type of items. I have 20 topics I want to cover, and I decide to use 35 multiple choice items in a 50-minute period. My research method students wish I would make that type of test, but I don't. There may be 1 question per topic area, and then a distribution of the remaining questions to the topics that are considered the most important. So when I am considering how I do content validity for this type of example, I would then want to look through and make sure that all of the items match up with the topics that I want. I would also want to make sure that I have a fair distribution of those items. I would want to make sure that everything is relevant, so all the items only measure the topics I choose to include. I would also want to throw out any items that are related to topics from previous content in the semester or content I don't plan on covering yet, or aren't related to research methods at all. So you have to take that all into account. Now, like I said, this can be done either quantitatively or qualitatively. Qualitatively, it's typically when you make a new measurement for research. It's usually done using the Delphi method. This you can review in a research methods textbook, but it includes having a couple of panel of experts look over your items and start from a really broad, just a research question of this is what you intend to measure, until you slowly start to define items round after round after round with this panel of experts. There's also a way that you can kind of do a cross-sectional study where you just measure get one measure from a larger number of experts, and there's quantitative ways to assess that. I cover that in my SEM class. The types of validity this type of validity is more commonly used with cognitive tests or scales, so affective measures. For the psychological or physiological domain, usually we use what's called face or logical validity. This is essentially you have a panel of experts that's looking at the test and making sure that all of it makes logical sense. So they're reviewing all the components and the procedures and the protocol to make sure it matches up with the science. The example I use often here is the timed up and go test or the tug test. The tug test is a measure of gait balance and gait speed, where it's used for older adults. Somebody is sitting in a chair with one hand on each of their legs. Time starts when they begin to stand up. Then they have to stand up, walk 8 meters, walk around a cone, walk back 8 meters, turn around, and sit back down in the chair. So the gait speed part comes in, and this is a time test. How quickly does it take to get 8 meters and back? Gait balance, not only do they have to hold the balance while walking forward in both directions, but they also have to hold balance while turning around the cone and while standing up and sitting down. All of those things would impact their speed or their time as well. So a longer time would suggest problems with both gait balance and or gait speed. That would be, any researcher who understands those variables would understand that as an example of face or logical validity. Relation to others falls under here too. Now, relation to others should shout correlation to you. This examines relationships between a new test and other variables. It can be done through criterion-related validity, convergent, and discriminant validity. Criterion-related, here the correlational procedures are used to measure the relationship between a criterion measure and a new test. This can be done both concurrently and predictively. So concurrently, done at the same time, predictively, predicts some sort of future performance. But what is the criterion? A criterion in this case is a standard by which your measure is being judged or validated. That would be a concurrent criterion, or a measure in which your measure is designed to predict. That would be future performance. So an example of concurrent here would be a reading achievement test. Students would take a multiple choice test on reading achievement, which is designed to measure achievement at the time of testing and not to predict any future behavior. It may be validated by comparing the scores on the test with the teacher's ratings of students' reading abilities, which in this case, that teacher rating would be considered the criterion measure. In predictive validity, an example here would be an employment test, where the purpose of the employment test is to predict success on the job. So people might take an employment test during their interview and then try to predict future performance. Well, in this case, what might be a useful criterion would be how they're doing in 6 months or a year, and it's very common when you're employed to have to undergo a 6-month review. So if you give the test to all applicants for the position, to validate it, for those hired, compare their test scores to their supervisor's rating at their 6-month review, and therefore the 6-month review becomes the criterion. If the employees scored similarly to their ratings, then we have predictive validity. So you can examine a strong correlation. You can assess either a strong correlation, or you could assess, since it's predictive, a regression. In convergent validity here is using correlational procedures to measure relationships between a new test and score and how they measure similar constructs. I'm going to make a big deal of similar constructs. So you're not going to correlate with the exact same thing, because it wouldn't make tons of sense to have two tests measuring the exact same thing, but they might be measuring something very similar. Measure the relationship between the new test and several other measures that assess a construct of interest. Before I sort of move on, the example I want to give for the convergent validity would be if you wanted to measure anxiety towards taking a test, then you could look at other tests taken, maybe it's taking a research test. You could look at just generalized test taking scores. You could look at anxiety measures. So does somebody generally have high state anxiety or trait anxiety? You could then also look to correlate it with other physiological measures, heart rate, skin conductance, and so on. In comparison, discriminant validity is looking at correlational from a different way. This involves various statistical procedures to measure relationships between new test scores and other measures intended to measure different constructs or measure the differences between samples that are known to be different. When comparing convergent and discriminant, convergent is looking to correlate the new test using the same trait with either the same method, so maybe measuring anxiety using two different paper and pencil measures. This is also called monotrait monomethod, mono meaning same, or it could be same trait with different methods. So we could have the same trait to anxiety scales, but behavioral indicators with a different method. So one could be paper and pencil, and one could be ratings by teacher. So often we look to do kind of a mix of monotrait monomethod with monotrait heteromethod as a way to increase evidence of validity. Discriminant validity is looking to do heterotrait, and it can be done heterotrait monomethod is probably the most common way to find evidence of discriminant validity, where you're correlating with different traits. In this case, we wouldn't expect high correlations, or in some cases we would expect no correlation. There are certain variables we do not expect to correlate, jumping jacks and IQ, per se. Besides correlational methods, the two other methods used are known groups. Here's where we have participants of opposites. So let's say that we bring in participants on a golf test, and we have our Division I golfers, it's a putting test, and we have our novice golfers, and they both complete our new putting test, and then they both take it. Ideally, the researcher is blind to who is the novice and who is the elite golfer, and we use a t-test to see if we can discriminate between the two people. And then, as we learned in class this semester, you can predict group membership through discriminant function analysis, where we could use multiple dependent variables. In this case, let's say we had number of subscales on our questionnaire to predict differences between groups. The final one, and this is going to be a couple of slides because it is a little bit more in depth, is called internal structures. The extent to which an internal structure of a questionnaire, and this is usually your cognitive or affective questionnaire, measures a construct of interest. This requires advanced statistical procedures called factor analysis. Again, this is when you often need to use the higher level of programming, and it explores the interrelationships amongst variables to discover if they can be grouped into a smaller set of underlying factors. So let's see how that works. Now, the two stats are called an EFA and a CFA, exploratory factor analysis and confirmatory factor analysis, and they have three overall goals: to explore the data for patterns and reduce the data into more meaningful chunks, into subscales. These are objectives of the EFA, is to explore and to reduce. Confirming, not surprisingly, is the objective of the confirmatory factor analysis, or the CFA. So you want to confirm the structure that you found in the OFA. So in order to find validity of internal structures, you have to do both an EFA and a CFA. Both require very large sample sizes and different samples. So you can't do an EFA and CFA on the same set of participants or subjects. You would need to get more participants or subjects. This is another reason why EFA and CFA is very difficult to do. So EFA attempts to explore the relationships among items to determine if the items can be reduced down into a smaller number of factors, assuming that all items are related to all factors until we have evidence to suggest otherwise. Visually, it looks like this. Let's say you had a series of items that was attitudes towards research scale, and there were items that were hypothesized to be either part of the verbal domain or through the analytical domain. The initial hypothesis is that all of these items correlate to both scales, until we have evidence to say that they only correlate to one or the other scale, which is the goal of an EFA. So we use that hypothesis to test, then we need to give some plan on which items or indicators go to which factors, and we do that by exploring factor loadings. That's what we're about to look at. A factor loading is a correlation of each item with each factor. So the items are those rectangle boxes that we looked at before. The factors were those circles, the analytical and the verbal. What we want is that correlation to be above 0.4, so a decent sized moderate correlation from item to factor. We would remove items according to 3 rules. If items don't correlate highly with any factor, if they load on multiple factors, meaning they don't adequately discriminate between factors, and they highly load on an incorrect factor, meaning we didn't write the item in a way that was clearly asking what we wanted it to ask. So if you look at this example, this is an example of the attitudes towards research scale with 3 proposed factors: verbal, mathematical, and oral presentation. The first step is to compute all of the inter-item correlation coefficients for the 11 items. Factor loadings are then computed by the computer program, and the following factor loadings are fictitious ones that clearly represent how they could be interpreted. Usually it's a little bit more difficult when we get real factor items. So item 1 is supposed to go on verbal. Now if we go down here, it's going to say that it loads really highly on factor 1, 0.78. And if we go down, it doesn't load well on factor 2, it doesn't load on factor 3, and it's not above 0.4 on factor 4. So right now we're pretty confident that, okay, it looks like factor 1 is going to be our verbal factor. Let's see what happens as we move on. Item 2 is also supposed to be a verbal question, but as we go down, it doesn't load on that factor 1 like the first one did, or 2 or 3, and it loads on factor 4. Well, as you look through, factor 4 only has 2 items that load on it, and we only hypothesized 3 factors, so we're not really sure what factor 4 is supposed to be. That could suggest that it's loading on the wrong factor and really not asking what we wanted it to ask. Item 3 was also supposed to be verbal. We see that it does load on factor 1, what we think is going to be the verbal factor, but it also loads on factor 3, what we think is going to be oral presentation. So that's going to be problematic and perhaps a not clearly worded item. Now let's take a look at a different item proposed to be on a different factor, oral presentation. Here, it doesn't load on factor 1, doesn't load on factor 2, but it does load nicely on factor 3. We're doing okay. For math, for item 5, it loads nicely on factor 2. We're doing well here. It does not load on any of the other items. Verbal loads nicely on factor 1. So again, 1 looks like it's supposed to be verbal. We have another math that loads strongly on factor 2. And then we have a third math. Doesn't load anywhere. So that item's not very helpful. Item 9, it only loads on factor 4, and you see how these 2 factors were meant to be verbal, but they load on factor 4, so it could be measuring some other different part of verbal, and then we're not really sure why. Number 10 loads on verbal presentation correctly, okay, or oral presentation correctly, that's good. Number 11 loads on verbal. You don't have to be able to break this down for the future, but you should sort of understand it, because you're going to read articles where EFAs and CFAs are presented, so sort of understanding the basis of where this comes from is going to be helpful. A CFA meets that third application to confirm the hypothesized structure. So you can see how we were building that structure in the last slide. We were seeing how each of these items correctly loaded on either verbal or presentation or math. Now we're going to confirm that we can do that again in a second sample using a second study using a new sample. So we can see that we're breaking down these items into each of the individual groupings, no longer assuming that they correlate to each things. Now, these little circles here just refer to error, much like they have all semester long, where we're assuming, just like I described in classical test theory, that every observed measurement or true measurement is some combination of observed plus error. So if this is our true verbal ability, the verbal comes from a combination of how we measure it using our question plus some error. CFA is going to use regression loadings, that lambda x that I referred to in an earlier video, to see if items significantly load onto intended factors. However, now that we're moving into higher level analysis and we're using different statistical programs, we're not using SPSS statistics anymore, we might be using M+, or AMOS, or Lisserl. We're getting slightly different statistics, and we're not really using p-values anymore. Instead, what we're going to do is examine overall fit of a model using fit statistics. So we do get those regression loadings. Again, we want them to be above 0.4, but then we also get this series of statistics. Again, not for memorization, just for your own edification when reviewing articles. Chi-square goodness of fit is really the only one where we look at a p-value. It should be greater than 0.05. It almost never is, because chi-square is so sensitive to sample size that pretty much every single CFA article you'll see that people will report that it's significant, and that's okay because it's sensitive to sample size, and they move on to these other indices of fit. So you'll notice kind of a pattern. The CFI, the GFI, the TLI, and the NNFI all ideally should be above 0.95. It's okay if they're above 0.9. There's some movement to kind of accept slightly lower indices, but Human Bentler in 1999 wrote an article that sort of created these cutoff values for what were considered good and excellent. So you want to see these numbers to be higher, closer to 1, ideally somewhere above 0.9 or 9 or above. Where you'll see these last two, which are measurements of error, not surprisingly, we want them to be small. The RMSEA, root mean square error of approximation, is the more commonly reported and is a little bit more mathematically solid. We want that to be less than 0.08. The SRMR, standard root mean residual, is sometimes reported, has a little bit more mathematical flaw. We want that to be less than 0.06. I'm going to give you a general scale of measurements to identify. These are mostly used with correlational or interclass measurements, but you'll see that even discipline-wise, these numbers aren't even strict. I more want you these come from the Nunnally and Bernstein article, or book. I just want you to see a little bit about them. But a couple of things. In reporting and reading about reliability estimate, usually it's better to just indicate what the coefficient was. For instance, the test-retest estimate was 0.83, so the reader can decide whether or not it's good or not, especially because different standards exist depending on the fields. When testing younger children, adapted students, beginners, and other special groups or populations, a researcher would expect lower reliability and validity, and that would be accepted. When testing affective measures, emotions, we'd also expect less consistency, therefore less reliability. But now, if you're in a more controlled setting, we would actually want higher reliability and validity standards because you can control so many mechanisms. And you can see here just a kind of comparison between reliability and validity. Ideally, you see these numbers above 0.7 is fair or adequate, 0.8 is good, 0.9 is acceptable. You see these numbers drop by a tenth when we get onto the validity side of things. The reason for that is that reliability is usually measuring the same variable to itself. It's an internal comparison, so we'd expect things to be really similar. Validity is an external comparison, measuring a variable to some other similar variable, or sometimes a very different variable. In other words, or therefore we'd expect it to be lower. In other words, reliability, we're comparing test to itself, test, retest, inter-rater, both the same measures. And validity, we're comparing to other measures, therefore more variation is acceptable. And that ends this video, and now you can move on to video number 4.